Okay. Sorry about the delay there. Here we go. So, last time in calculus class. All right, I don't want to do too much there. I think we covered everything. Yeah, well, I really wanted to cover there. But let's go back to this particle motion stuff because, man, that was a lot of information thrown at you here. A lot of stuff to consider, and this is definitely something that you want to make sure that you've got down, okay, pretty solidly, okay, for, future questions. In fact, it's what we're going to be doing here today, okay? So it'll be helpful to kind of review this just a little bit today, okay? One of the big applications in which we will be, or one of the big contexts that we'll be using when we are using some of this calculus, we've been talking about the derivative and stuff, is in particle motion, okay? And specifically we deal with particles, so that way, it's like you don't have to worry about like more like real worldy kind of stuff with like gravity and mass and friction, and we're just going to have like these nice little particles and make them very simple so we can just have position, velocity, and acceleration of them and not have to worry about like all these other like weird environmental constraints and stuff like that. Anyway though, so the three contexts, right, are all related by being the derivative. So position, okay, the original kind of function where, the location of your particle, its derivative or the rate of change of position is the velocity, right? And so that would then result in the fact that the position's derivative is the same as the velocity of that particle, okay? And then taking the derivative or the rate of change of the velocity results in talking now about the acceleration, which is then the derivative of velocity is acceleration. And since the first derivative of velocity is equal to acceleration, that would mean the second derivative of position would be acceleration there, okay? Typically, when we're talking about a particle, the particle is moving along the x-axis, okay, at any time t, okay? So it's just moving like left and right along the x-axis, and the position would give its position on the x-axis, and then velocity and acceleration, of course, at those different times. Okay, so again, we have lots of meaning here, right? Initially means when t is 0. At the origin means when your position is 0, right? At rest, that means the particle is not moving, would be when the velocity is 0. Okay, a positive velocity indicates your particle is moving to the right. Velocity that's negative indicates moving to the left. Again, so velocity has this directional component to it in addition to, it being just a value. Average velocity, here is a key one here, okay? I'm going to highlight this again. Average velocity, okay? We may be tempted here to do the slope, okay? Because again, when you see the word average, you should think slope formula, okay? We may be tempted to do like subtract velocities on top divided by subtract, time on the bottom, right? But that's not the case. Average velocity, okay, is the same thing as asking for the average rate of change of position. Since we're looking for the average rate of change of position, it's the slope applied to position, okay? The rate of change is the slope part of the position. So it's average rate of change of position, it's the slope formula. So maybe I can even add on to this, like x of like t1 minus x of t2 over t1 minus t2. Okay, it's a position that you're going to subtract to find an average velocity. Okay, and again, it kind of describes that here as well in the sentence. Whereas instantaneous velocity, that is x prime of t, the derivative position, or you can just say v of t. Okay, instantaneous velocity is the value of the velocity at a specific point. Okay, or in other words, it's the derivative of the position. So again, in symbols, but in words right there. Okay, and then acceleration, if it's positive, the velocity is increasing. If the acceleration of a particle is negative, the velocity is decreasing. Okay, or getting more and more, approaching more negative there. In order for a particle to change direction, the velocity must change signs. Speed, okay, is related to velocity, but speed basically removes the direction component of velocity. Speed is always positive. Okay, you always just make speed positive. It's the absolute value of velocity. Okay, that's why again, if you're going forwards down the highway, at 50 miles per hour, or backwards down the highway at 50 miles per hour, your speed will be 50 miles per hour, right? So it doesn't matter. But if it's talking about velocity, then those can have positive negatives to it. Amount of ground the particle covers is the position. The change in the final position, initial position, is the net change in position there. And the particle speed, and this is a key thing too, that this is maybe a difficult concept as well. The particle speed is increasing when the signs of the velocity and acceleration are the same. That means, and this makes sense, of course, you'll buy this easily when I say, if the velocity is positive and the acceleration is positive, you're like, of course, Mr. Widmeyer, the speed is increasing, right? Because your velocity is increasing. But By the same token, if the velocity is negative and the acceleration is negative, that means your velocity is getting more and more and more negative. But take the absolute value of that, that means it's increasingly getting away from zero, right? You can think of it this way, right? Think about a graph of velocity over time. So there's time, and here's like the velocity, right? If your velocity is positive and your acceleration is positive, that means your velocity is going up like that. So that's like v greater than 0, a greater than 0, right? You're speeding up away from a velocity of 0 right here. There's like a 0 velocity at rest. But if you have a negative velocity, so you start down here, and then your acceleration is negative, you're going to be also speeding away, you're right, speeding up away from that 0 velocity there. So that's the idea. Hello? Sure, no problem. Bye. Zoe, you're wanted in the AP office for something. Okay, so here's situation. Again, this is v is less than 0, right? Negative velocity. You can see it's below the kind of t-axis there, and acceleration is less than 0 as well. Okay, so both of these things result in speeding away, right, away from that 0 velocity. Okay, questions on any of that before we move into these questions on the other side? All right. So again, if you feel like you still have a question, you don't get it here, feel free to ask here as well. All right. So back to what we talked about yesterday, we have this table here with some given time moments, instances, and then instant velocities at those times. Letter A, we already determined at t equals 0, the particle is moving to the left because velocity at 0 was -3, so the velocity, since the velocity is negative. Yeah, okay. So letter B, is there a time 0 less than or equal to t less than or equal to 12 minutes when the particle is at rest? And again, I put this in here as a little note for ourselves, and you can do this too, right? When you see this, do the interpretation. What does that mean, v of t equals 0? And we said, I think it was, Simeon, were you saying that yesterday, I think? Was it you that decided that there was a 0 here somewhere, the velocity? Who was it? Bryce. Okay, Bryce. Sorry, I knew it was over in this direction. So Bryce, what did you say here? Did we have a 0 velocity here?
Yeah.
Yes. And where did it occur?
Somewhere between the start and 2 minutes.
Yes, exactly right. And and you knew that because. Exactly right. Intermediate value theorem states here that since our velocity goes from -3 to 2, v of t goes from -3 to 2 between the times 0 and 2. There must be some time between that where the velocity is going to be 0 as well. Exactly right. So, how do we explain this? Well, okay, so we're going to use the intermediate value theorem here, and so basically we need to establish, well, one big thing we have to establish is that our function is continuous, right? Okay, so since v of t is differentiable, okay, v of t is also continuous. Okay? So I want to establish that first, or establish it somewhere in your argument, right? You really should, because that's a prerequisite for using and applying the intermediate value theorem here. Okay? We're told the function is differentiable, so therefore it's also going to be continuous, right? That differentiability implies the continuity. Okay? Also, since, and then here is where we want to say something like, I don't know, I'll say like v of 0, we're talking about our y value there, which is equal to -3, is less than 0, which is less than v of 2, equal to 2. Okay. So I'm establishing that our two y values there, -3 and 2, are two velocities, right? One's negative, one's positive, and 0 is between it. Then there is some t such that 0 is less than t is less than 2. So now I'm saying my x value there between the 0 and 2. And such that, and this maybe isn't the best way to say this, but anyway, and such that, not f, v of t equals 0 by the intermediate value theorem. okay? So again, what are we doing here? We first establish that the function is continuous, right? That's necessary to even think about using the intermediate value theorem, okay? We also establish that the value that we're trying to guarantee exists, right? Is there a time when the particle is at rest? We're trying to show here, okay, 0 is between two y values, okay, two successive y values in our function there, okay? We establish that. Then, and then we can use the intermediate value theorem idea. Then there is some t that, you know, t between the 0 and the two x values there, such that v of t equals 0. And then you can just say that's by the intermediate value theorem, okay? So I'd say that's a pretty good, you know, kind of like succinct way of putting it. Could you say it in more words than that? Absolutely. Could you say it in less words? Maybe, okay? Could you say it a little bit prettier than I did? Probably, okay? But I think that covers all of our bases there, all right? So, questions on letter B? All right, let's keep going here then. C, what is the average acceleration of the particle over the interval from 2 less than or equal to t less than or equal to 5? Okay, so we see that word average, okay, and acceleration. All right, we know nothing about the acceleration here. All we're told about is velocity, right? But acceleration, we can also think of that as the rate of change of the what? Velocity, right? Acceleration is the rate of change of velocity. So maybe instead of thinking as acceleration, think of it as rate of change of velocity. Now that we have that, when we're looking for the average rate of change of something, what do we use to find the average rate of change of something? Slope. Slope formula specifically, right? Over the interval 2 to 5. So all we're going to do here is just do v of 5 minus v of 2 over 5 minus 2. It's just a slope formula. Okay, it's just the slope formula there. Okay, for the interval from 2 to 5, I'll say. Okay. Just a slope formula. What's v of 5? 3. What's v of 2? 2. And then 5 minus 2 is 3. And so we get 1/3. Are we done? No. What do we need still? Indicate units of measure. Okay. It's easy to do this. What are our velocity units? Yeah, we've got it right there. Meters per minute. So it's 1 meter per minute. And then what was our time unit? Minute. Okay, so 1 meter per minute over minutes is really 1/3 meter per minute squared, right? Meter over minute divided by minute is going to give you meter per minute squared there. And that's your acceleration. Okay, 1/3 average rate of change of velocity, or the average acceleration. Okay, that's it. We just use our interval there. Questions on that? Okay. Use data from the table to find an approximation for v prime of 10 and explain the meaning of v prime of 10 in terms of the motion of the particle. Show your work and indicate units of measure. Okay, so v prime of 10 is the same thing as asking for what? What's the derivative of the velocity describe? Acceleration. So this is essentially saying describe the acceleration at 10. But of course, all we have is information about the velocity, right? We want to know the instantaneous acceleration at 10, but we're going to approximate. Okay? We want to approximate. Okay. If we can't find the precise value at 10, how can we go about approximating what the acceleration would be of 10, or the rate of change of the velocity? How can we approximate that at 10? You don't need to use a limit, no. To approximate a tangent slope, right? We're trying to find a tangent slope here, v prime of 10. What can we use to approximate, or what have we used in the past to approximate a tangent slope? I heard it. Secant. Secant slope, okay? So this is an approximation for v prime here. Since again, we don't have anything about 10, any information about 10, we can just find the slope between 2 points, right? We can't find the value of the derivative at 10, but since we're trying to do an approximation, we'll just do the slope, okay? The question is though, which 2 points should we pick here from our table to approximate v prime of 10? What's that?
8 and 12.
Why 8 and 12?
Because it's in between them.
Because 10 is in between them. Exactly right, okay? So the value of the derivative at 10 of v should be closely approximated by the points that 10 would be between, right here. So 10 would be between these 2 points, so guess what? It's just a slope formula again, okay? So we'll just do v of 8 minus v of 12, or v of 12 minus v of 8, whichever one you like there, okay, over 8 minus 12. Okay, so again, v prime of 10 is approximated by secant slope between v of 8 and v of 12. Okay, v prime of 10 is approximated. Again, we're approximating, so you're going to use a secant slope to approximate a tangent. Okay, v of 8 is 7, v of 12 is 5, 8 minus 12, negative 4, and so 2, and then over negative 4, so negative 1/2. Okay, what would our units be here? Meters per minute squared. Okay, again, if you're not sure about that, the numbers on top, that's a velocity. That's in meters per minute. You're dividing by minutes. Meters per minute divided by minute, meters per minute squared. Okay. Are we done? Explain the meaning of v prime of 10 in terms of the motion of the particle. Okay? What is this negative 1/2 telling us about the motion of the particle here? Again, we're approximating v prime. We just said that v prime is another name for the what? Acceleration. So what is this telling us? The acceleration at t equals 10 is approximately negative 1/2, okay? Okay, is that all we can say here? Is that all we can say here? And you're like, probably not, Mr. Whitmire, because you're asking that stupid question. All right, there's more we can say here. What do we know about our velocity in that interval? It's what?
Slowing down.
It's slowing down, and it's so the velocity will be positive here, and so yes, as an overall result, we can say the velocity of the particle is going to be decreasing, or this, I should say, the speed of the particle is decreasing. You could say that, okay? Well, if you can say the speed of the particle is decreasing here. Why? Go back to what we talked about here. The particle speed is increasing when the signs of the velocity and acceleration are the same. The particle speed is decreasing, like Mario said there, when the signs are opposite. But Mr. Whitmire, what's the sign of velocity? Well, our velocity here goes from 7 to 5, so we can even see the decrease in speed there, but they're positive, right? By the intermediate value theorem here, well, we're going to hit every value between. I guess it could go negative potentially there, but it looks like we are slowing down, okay? So the particle speed decreases overall from, what is it, t equals 8 to t equals 12 minutes. I'm running out of space here. Okay, we can say that here. So acceleration at t equals 10 minutes is approximately negative 1/2 meters per minute squared. But the particle speed decreases overall from time t equals 8 minutes to time t equals 12 minutes, right? We can see it happening there. Okay? All right. Letter E, last thing here, is the maximum velocity of the particle at t equals 8? What do you say there? What do we say? Are we guaranteed that the maximum velocity of the particle there is happening at t equals 8? What's that? No, right. Okay, so why not? Why can't we say it? It's the highest number. We don't know what's going on in between. Very good, both of you. Yes, exactly right. Okay, is maximum velocity of the particle at time t equals 8? Explain your reasoning. Not necessarily. We do not know the values of the velocity in the intervals between our given points. Something like that. Okay? Questions on any of that? All right, turn the page. So, and the first problem there, we had to like kind of pull information out of a table. Another popular way to represent these situations, these scenarios, is to be given a graph as well. Okay, so in this scenario, the graph below represents the velocity. Okay, so this is v of t in feet per second of a particle moving along the x-axis. So this is not the particle's motion here, right? This is not the particle's motion. You are not looking at how the particle moves. The particle does not go up and then down and then flat. This is the velocity, okay? This is the velocity that you're looking at here, okay? So for this interval from 0 to 9, okay? So at t equals 4 seconds, is the particle moving to the right or to the left? Explain your answer, okay? So think about that for a second or two, okay? T equals 4 seconds. Is the particle moving to the right or to the left? And let's go to Shelby. What do you say, Shelby? Oh, God. What is the value of the velocity at time t equals 4?
It is
5, okay. So that means the velocity is positive, right? So if the velocity is positive, can we say the particle is going to be moving to the right or to the left? Yeah, a positive direction to the right, exactly right. And that goes back, again, to our little paper right here, right? If the velocity of the particle is positive, then the particle is moving to the right. If the velocity of the particle is negative, then the velocity is on the particle is moving to the left. Okay, that's all we need to use there, yeah. So, since v of 4 is equal to 5, which is greater than 0, the particle is moving to the right. Okay. Again, recall here that it says this graph is representing the velocity of a particle that's moving along the x-axis. Okay, sorry, I was off the screen there. A particle moving along the x-axis, so that particle is moving left and right, but here's its velocity. Okay? All right. Over what time interval is the particle moving to the left? Explain your answer. Okay, so take like a minute or 30 seconds there and take a look at that. I'm going to call on someone. Okay, so looking at that graph there, over what interval would we expect our particle to be moving to the left? We just, had Shelby identify that at 4, the velocity was 5, and so we knew the particle was moving to the right. So what's the interval for when the particle is moving to the left? Okay. So Lily, do you have an answer for that?
I said 0 to 9, but not including 0.
Okay, so you said 0 to 9, but not including 0. That means the particle is moving to the left.
Oh, wait, I'm sorry. So that's the y.
Yeah, just the left. So when is the particle moving to the left?
5.
5 to 5 to 9.
X.
Yeah, exactly right. Okay, and sorry, and how did you know that was why it was moving to the left? What were you looking for there?
What?
What were you looking for there? Like, how did you know that was the interval that you wanted to?
X-axis and some negative.
Yeah, okay, the velocity is negative on that interval. So I'm going to use the interval 5 to 9 like that. Because v of t is negative on that interval. Okay? All right, next question.
Is 9 supposed to be a closed bracket?
That's a good question.
It stops.
It does stop there. So, well, or like we don't have any more information after that. I want to say that you could include it here. I want to say that we can include it, yes. Okay, but definitely not the 5, right? Because at 5 it would be at rest. Yeah. So, all right, letter C. Moving on here. Good question. Find the acceleration of the particle at time t equals 2, 3, 4, and 7 seconds, or state that does not exist. Okay. So we have the velocity, and we're trying to determine information about the acceleration. How is the velocity related to the acceleration? The acceleration is the derivative of the velocity. So when we look at this picture, we want to think about the derivative of the velocity at these certain times. Okay? So at time t equals 2, here we are on our graph. That's the value of the velocity, right, is 8, but that's not what we want. We want the acceleration. What is the slope at this point? 2, right? It's up 2, right 1, up 2, right 1 there. So yeah. So let's see here. A of 2, we'll say, is equal to 2. Okay. What about A of 3? Or the slope does not exist. Great. Exactly right. Why doesn't it exist? Because 3, yeah, the slope suddenly changes here at 3, right? The slope goes from positive suddenly to negative, and so the limit would not exist there for the derivative, okay? And so you're right, yes, that point there, okay? Very good, very good. All right, how about A of 4? What's the slope? What's the slope of the velocity at 4?
-5.
Is it -5? Okay. And then how about A of 7? 0. Very good, okay? It's constant there, okay? So great, there you go. Okay, don't need to worry about units there in this case. It doesn't state units. We could give units though. It would be feet per second squared for any of those. Okay, I'll just put it for 1. Okay, because again, if we had velocity is feet per second, then acceleration would be feet per second squared. Okay. Is the particle's speed increasing or decreasing at time t equals 4? Okay, so remember to determine whether the speed is increasing or decreasing, okay, we need to think about 2 things, the velocity and the acceleration, right? If you go back to what we talked about here, a particle's speed is increasing when the signs of the velocity and acceleration are the same. The particle speed is decreasing when the signs are opposite. So, what is the velocity at 4? It is 5. Okay, and what is the the acceleration at 4? We said it was -5, right? So velocity is positive, acceleration is negative, therefore the speed is what? Decreasing. Because, what could be a good reason here? The signs of the velocity and acceleration are opposite, yeah. Okay, good. All right. Questions on any of that so far? Okay. And again, you can kind of think of these things as like if the velocity is positive and the acceleration is negative, those things are kind of counteracting one another, and so it's going to bring the speed down, right? If the velocity and acceleration are both positive, if the velocity and acceleration are both negative, they're going to be, the acceleration is going to be, increasing the velocity or decreasing the velocity more and more away from that velocity of 0. Okay, letter E. And again, here's this thing. We've got to be careful with this. Average acceleration of the particle over the interval from 2 to 4. Okay? Instead of thinking of this as average acceleration, instead of using the word acceleration, we could use rate of change of the velocity. So you can if you want to help yourself out here, average rate of change of velocity. Okay, I'm going to abbreviate there just to save myself some space. So in other words, if we're looking to do an average rate of change, we need to use the what? Slope formula, or a secant line slope kind of thing. Right, okay? So this is literally just v of 4 minus v of 2 over 4 minus 2. Okay? And so we said v of 4 was 5, right? V of 2 is 8 over 2, so we get negative 3 over 2. Indicate units of measure here. What would our units of measure be? Feet per second squared. Right. There it is. Okay, questions?
Could you also just look at the graph and then just...
Yeah, you could absolutely just like count the slope you're saying or something. Yep, absolutely. Okay, v of 4, so this point to this point, and just count the slope, you know, down 3, right 2, and see it that way. Absolutely. Okay. My only concern with that is showing the computations that lead to your answer. I'd be like, how are you going to show that? But they don't always put that in there too. So that would be absolutely a good strategy to use though. Okay, next one here, number 11. Now we don't have a graph. We don't have a table. We've just got a function here. Okay, we just have a function. All right, so make sure we're doing okay here. Yeah, okay. So this one, all right, this is non-calculator active. Now the next one is calculator active, okay? So we'll see if how much we can get done here since we are running short on time, but we'll go. All right, so a particle moves along the x-axis so that at time t its position is given by x of t equals that. So now we're given the position of the function. Okay, bless you. Okay, so the first thing asks us to find the displacement of the particle over the time interval from 1 to 3. Okay, so the displacement, or we can really say the net displacement there. Okay, so this is simply taking our final position and subtracting our initial position there. Okay, the position at 3 minus the position at 1 will get us the net displacement there. Okay, starting position and then the distance to that stopping position. Okay, that's all there is to it. And so x of 3, let's see here, it's going to be what, I guess I'll plug it in and make it 3 squared minus 5 times 3 plus 4 minus 1 times 1 squared minus 5 times 1 plus 4. Okay, so that's nice because the 1's kind of, you know, cancel out there and give us 0. Okay, so and then here, sorry, I just wanted to refer back to our table thing. Remember, this is coming from the idea here, the change in the final position and the initial position is the net change, or net displacement. You can also think of that too, net displacement. Okay, all right. So anyway, simplify this here. This is all going to be 0 because it's 1 minus 1, so that just equals 0. Let's see, that's going to be 2 times 3 squared is 9 minus 15 is negative 6 plus 4 is negative 2, so times negative 2, which is then, so negative 4. Yes? That was what we got there. Okay. At time t equals 1, is the velocity of the particle increasing or decreasing? Okay, is the velocity of the particle increasing or decreasing? What determines whether the velocity of the particle is increasing or decreasing? What concept determines whether the velocity is increasing or decreasing? What thing determines whether the velocity is increasing or decreasing? It's the acceleration. Acceleration. Okay? Specifically, if the acceleration is positive, we can say that the velocity will be what? Increasing. If the acceleration is negative, we'll say the velocity is decreasing, right? So, great. All we have to do is then just find the acceleration at time t equals 1. How can we go about finding the acceleration at time t equals 1? The derivative of position, which will give us the velocity, and then we'll have to derivative of velocity. Okay, now, if we look at this, option 1, if we go to take the derivative of the position, what could we do? So we can multiply it out first and then take the derivative, or we could use the product rule here. They both look kind of crummy to do, right? Product rule here is going to be like, ugh, and then the multiplying it out first is kind of, ugh. I'm going to multiply it out first. I think. I think that's going to be the best use of our time here. And I'll explain maybe why if I have time in a little bit here. So we'll distribute the t through everything here. So that's going to be t cubed minus 5t squared plus 4t. And then distribute the minus 1 through everything. So minus t squared plus 5t, bless you, minus 4. Okay. You can combine like terms at this point. Maybe not a bad idea. So let's see. T cubed, minus 6t squared plus 9t minus 4. Remember here, this is still the position, right? This is still the position. We're just rewriting it to make it a little bit more palatable. Okay. All right, and then the velocity function, well, now it's easy. It's just a polynomial here. So with what, 3t squared minus 12t plus 9. And so then the acceleration would be 6t minus 12. And so now I can just evaluate the acceleration at 1. Okay, so negative 6. So is the velocity of the particle increasing or decreasing at time t equals 1? Decreasing. So the velocity is decreasing at t equals 1 second. Oh, you know what? It doesn't give time units here, so never mind. I can't say seconds. So just t equals 1, we'll just say, because a of 1 equal to negative 6 is less than 0. Okay. You can just say because a of 1 is negative, that's fine here. I write it kind of a certain way every time, but as long as, again, you're given that same kind of information, however you want to word it is your choice. Okay. Questions up to this point? All right. Did anyone try and do this with a product rule? Okay. So, a product rule would work here. Wouldn't be too bad, I don't think, but then within that velocity, you'd have another product rule to do too. So I think it's just a little bit more work. I think this was probably more worth our while. And again, that's something that you'll get a feel for. The more calculus that you do, you'll get a feel for like, do I want to do a product rule here, or maybe do I want to multiply it first and then do a product rule? Okay. You'll learn, be more efficient and stuff like that too. All right, letter C, final values of t for which the particle is moving to the left. Okay, what do we use to determine if the particle is moving to the left? Velocity, specifically when the velocity is what? Negative. Now, we already have the velocity calculated right here. So, 3t squared minus 12t plus 9. How can I represent I want to know when this thing is negative? Less than 0. We're going to use an inequality here. Okay. Remember these? We talked about these kind of inequalities in our prerequisite stuff. Okay. So, what should we do from here? How do we start solving this? Factor. So let's factor out the GCF of 3 first, just to make things a little bit easier for ourselves. Okay. Does this thing factor? It does. Okay. Okay, we factored it. And remember what we do now? Yeah, we kind of like make a little number line here, right? So t equals 3, t equals 1 are going to be our zeros. So I'll put 1 and 3 on my number line, okay? 1 and 3 on my number line here. Okay, and now that I've made that number line, what do we need to do now? Pick some values in the intervals there and then plug them in to see what kind of sign we get. So let's just use 0, okay? So plugging in a 0 here, 3 is always going to be positive, right? Don't forget there's that 3 coefficient there, okay? Don't forget that 3 coefficient. So it's going to be a positive. 0 times minus 3 is going to be a negative, and then 0 minus 1 is going to be negative. So what's a positive times a negative times a negative? It's overall positive, okay? So not in that interval. All right, let's pick something in here. Let's do 2, okay? 3, positive. 2 minus 3, negative. 2 minus 1, positive. Positive times a negative times a positive. Negative. Aha. So between 1 and 3. And then let's try another 4 here. 3 is positive. 4 minus 3 is positive. 4 minus 1 is positive. Positive times a positive times a positive. Positive. So what are all the values of t for which the particle is moving to the left? Between 1 and 3. Okay. Do we include the 1 and the 3? No, because at 1 and 3 it's 0, right? So, you can do like an inequality if you wanted to, a compound inequality, or you could just give the interval there as well. Okay. All right. Find the velocity of the particle when the acceleration is 0. All right. How should we go about approaching this one? What should we do? Set what equal to 0? Acceleration, right? So that's not too bad. Okay, 6t minus 12 equals 0. Okay, so here just again, just to like to pause real briefly here because we're kind of like blowing through a bunch of stuff, but to pause real briefly here, right? Here we have a situation that's not that bad, right? What we're trying to solve for. But where is the difficulty? It's in the interpretation, right? So like half of the work here is just in this dense, meaning interpreting the sentence that we're given here, right? Being able to say, okay, acceleration, what was that? Okay, that was what we got back here. We're going to set it equal to 0. And then what? Are we done? No, we got to plug it back into the velocity to figure out, that velocity. So anyway, we get t equals 2 for the acceleration. And then we just do v of 2, which is equal to 3 times 2 squared minus 12 times 2 plus 9. Okay? Do I need to simplify any further? Nope. It's all arithmetic. I can circle that answer and say, there it is. That will be the velocity. Okay. Alrighty. Questions on any of that? All right, we got 5 minutes to get through this one. Okay, if you got your calculators handy, let's get those out. All right, we'll just go right up to the bell here. All right, the homework will be on the Google Classroom. I see trig in the function, so that means we need to check what about our graphing calculators? That they are in radians. Right. Okay, very good. Mine is in radians. Okay. Okay. Let's read through here the directions. A particle moves along the y-axis. So now, when I'm talking about a positive velocity, that means our particle will be moving in what direction? Up now, right? A negative velocity means we're moving down now, okay? So just that little orientation change there. Okay, so there's our equation. Find the velocity and the acceleration function. Okay, so we can actually do this without our calculators, right? Okay, so we'll do that here real quick. So y prime of t is going to be what? 12.06 t plus derivative of sine is cosine, so 9 cosine t, and the derivative of e to the t is e to the t. So there's the y prime of t. I'll say that's v of t as well, equal to that. And then the acceleration would be the derivative once more, okay? And so the derivative here would be derivative of 12.06 t, 12.06. Derivative of cosine is negative sine, so we minus 9 sine of t. And of course, derivative of e of t, our friend there. So easy to take that derivative, e of t. Okay? Find the initial position, velocity, and acceleration of the particle. How will we go about doing that? Initial means what? At when t is 0. Okay? So again, we won't run through that. I think we can get that here, right? But just basically, for position, you want to just find y of 0. And then for velocity, you would want to find v of 0. And then for acceleration, you would find a of 0. And again, that would be using your calculator. Actually, you don't really need a calculator for any of those particularly. What would our units of measure be? For the position, what would it be? Meters. For the velocity, what would it be? Yeah, watch your time units at second. So meters per second. And then the acceleration, what would the units be? Seconds squared. Good. Okay. What is the velocity of the particle and the acceleration is 0? This is, I think, where we need our graphing calculators. So we would first, what would you do first here for letter C? Yep. A of t equals 0. T equals something there, right? And then step 2, what would you do? Plug that velocity, that t value into the velocity there and get your answer. Okay, and again, this is just because we're running out of time, so I wanted to kind of briefly go through this. When is the particle moving up? How will we figure that out? Inequality when what is greater than 0? Velocity. So find intervals when v of t is greater than 0. Justify your answer. Your justification would be because the velocity is positive on these intervals. That would be your justification. Okay? All right, we'll stop there. Give you guys a couple minutes, a minute or two there to get everything back together. All right, if you want to work through these, okay, I will work through these too, so you can see them on Monday when we come back, but there is a homework assignment too. This is not homework. I won't collect this, but if you want to work through them there yourself, just give yourself some extra practice, okay, because the book doesn't have a whole lot of great examples of these, so give yourself some practice with this, try and finish these up, and then, of course, the Google Classroom will have your actual homework, okay? That was exciting.